Hey guys, so today we're going to be talking about the Doppler effect. So what is the Doppler effect? Well, let's start with an example. So let's say you have a police car. Got its siren. And you are standing off to the side, right over here. That's you. And the police car decides it's going to turn on its siren. So it's going to emit sound waves at a frequency, let's just say F3. F3 being just some random frequency of the siren. But first, to explain the frequency of the siren, we need to understand what is sound. So what is sound? Sound is simply a wave with an amplitude of this distance, and from trough to trough being the wavelength, and we denote that by lambda. So there's an important formula that relates wavelength, velocity of the wave, and frequency. And that formula is velocity equals lambda times your frequency. So in this case, your frequency would equal velocity divided by your lambda. So what is the v here? The v is simply the velocity of the wave through a medium. And one important thing to note is that velocity does not change if the medium doesn't change. And in all these problems, we are going to assume that the medium is just air, and that has a velocity of 343 meters per second. Okay, so let's go back to our police car example. All right, so the siren of the police car emits a sound at F. That's just the frequency, we're just going to call it F. And then you are going to be off to the side. Both of these objects are not moving, and that's important for this first example. So we said previously that the velocity was 343 meters per second. And that's going to be equal to our wavelength times our frequency. And remember, we just said F is a constant that's given. This is just a general example. So in this case, our wavelength is going to be wavelength times our F. And to solve for wavelength, all we got to do is divide by F. We have 343 divided by the frequency equals to our lambda. Okay, so that example strictly covers stationary objects. So what happens if the object starts moving? So let's go back to our example. We have our police car, and we have you, except this time the car is traveling at a speed of 5 meters per second towards you. 5 meters per second. This, in effect, shortens the wavelength. So instead of being a nice circle like before, now the wavelength's can be more elliptical, where the sound waves look more like an oval, with it being more bunched up towards the direction it's traveling. So with this shortened wavelength, what happens is that the frequency must increase. Not the frequency from the car, that always remains the constant F. However, now there is a new frequency observed, and that is actually going to be higher than the frequency of the car. And that is because if the wavelength is shortened, because the car is now moving at a perceived higher speed than the original speed of the wave through air, then our new frequency observed must increase in order to make up that difference. I drew that wrong, just cross that out. So it's the elliptical in the other direction. So the longer wavelength is now going to be on this side of you, since the car is now traveling at this way at 5 meters per second in the opposite direction away from you. So the wavelengths will be short at the front of the car and then longer towards you. So what does this mean? You still have your frequency observed and your F. Now what's going to happen is that the frequency observed is now going to be lower than our original frequency. And you know this is true because whenever you are, let's say, walking on the sidewalk or in a car, and a police car or a fire truck or an ambulance flies past you, you notice that the pitch changes, the frequency changes as they pass through you. So the Doppler effect has a critical equation that allows you to solve these simple problems. So you have your F naught, which is your observed frequency, V, which is just the speed, which is the speed of the wave in the medium. So in this case, it's 343, plus or minus the velocity of the observer. So this is in this case that where you would move to the left or to the right, and it's plus or minus depending on if you're moving towards or away from the source, and then divided by V. It's the same as the speed through of the medium, plus or minus the velocity of the source. And in our examples that we covered, we changed Vs, which is the speed of, in this case, the car, and that's going to be all multiplied times the original frequency. And using that equation, you can solve many types of Doppler effect equations. And let's get started with them. Okay, so for this problem, you are walking towards a speaker at a speed of 6 meters per second. And the speaker is emitting sound, it's not moving. And this speaker emits sound at a frequency of 1000 hertz. So we take our Doppler equation, which is our F observed equals V plus or minus our velocity of the observer and velocity plus or minus velocity of the source, all times our frequency. So time to start plugging in some values. We said earlier that V is always equal to 343 meters per second. So plug that in, 343. Now, plus or minus the observer's speed. So we know that the observer is walking towards the speaker. So what is that going to mean? It means that the velocity needs to be positive. Divided, plug in your 343. And remember, we said that the speaker is stationary, it doesn't move, so that's just going to be a plus 0. And then our frequency of the speaker is going to be 1000. Now you can just plug that into your calculator, and once you plug into your calculator, you get 1017 round up to 0.5 hertz. Now let's conceptually think if this is right. Now remember, we said that if the objects are moving closer to each other, then our observed frequency should be higher, and in that case our observed frequency is higher than the original. Alright guys, thank you for watching and supporting my channel. Don't forget to smash that like button.